Well, the Pacific water plays really crucial role in controlling the heat and sea ice extent in this part of the Arctic. And there is a very good confirmation for that from oceanographic observation. This is a time series of Pacific water content in the upper layers in the area north of the, this is the Bering Strait, this is the shelf, and this is the deep ocean. So north of Alaska, north of the Chukchi Sea, you can see an increasing content of warm Pacific, relatively warm Pacific waters, which have a quasi-decadal oscillations that definitely affect sea ice conditions. This is a very beautiful example, very graphic. It shows us how the tons of warm currents coming from the Pacific literally eat out ice on their way. You can see there are three major branches of Pacific waters coming through the Bering Strait, and each of them just melts ice as it goes into the central Arctic Ocean. So this is really very, very important. And in addition, of course, a large part of that is controlled by local atmospheric factors in the North Pacific, like the Aleutian Low. Same system as Masanobu has just shown us for the Pacific Decadal Oscillation, Aleutian Low. That system strongly affects flow of water into the Arctic. But also, the warming climate increases the overall flow due to the intensified steric effect, because there is a stronger transport of water vapor from the Atlantic Ocean into the Pacific as you warm the Earth altogether. And then there is a stronger transport of this additional moisture from the equatorial areas to the polar areas. And that increases just the sea level in the North Pacific. And due to the steric effect, this water flows faster into the Arctic. So with warming climate, we're having more Pacific relatively fresh water getting into the Arctic Ocean. And through the Arctic, through the Canadian channels, it gets into the North Atlantic. A very interesting example is that just recently, within the last 10, 15 years, biologists started finding Pacific species in the plankton in the North Atlantic, which have not lived here for 2 million years. So Neodenticulus semina is the diatom that got extinct in the North Atlantic with the beginning of glaciations in the early Pleistocene. And it is appearing there now. And that has to be only due to this kind of passage of Pacific waters through the Arctic and into the North Atlantic. So this is really, really very interesting. And of course, this system could operate only when the Bering Strait was open, and the Bering Strait is only 45 meters deep. So when sea level was lower than today, you didn't have this connection. There was just a land bridge instead of a Bering Strait. And that's most of the time. If you look at this is the reconstructions from the last glacial maximum, the lowest sea level was minus 120 meters. So there was a huge land bridge here, Beringia, with mammoths walking over it. And then during deglaciation, it was getting more and more, little water was getting higher and higher. And then only in the Holocene, during the last 10, 11,000 years, the Bering Strait finally got open, and this area was flooded, and the circulation resumed between the Arctic and North Pacific. This is a very good example of how much non-analog conditions we had in the past, and therefore how important is it to study what was here in the past if we want really to understand the long-term history, that we cannot rely on the observations of a few decades or even centuries. Well, another big joker in the Arctic is Greenland, of course. This is not the ocean, properly speaking, but it's still the Arctic system. And as you know, Greenland is melting very fast. There was some kind of a slowdown within the last several years. Nevertheless, the anomalies shows us that the melting continues and it does increase. And what is especially interesting for us, and that's another important aspect of the studies that I'm conducting, is that a large part of this loss of Greenland ice occurs through the speeding up of glacier drawdown through the fjords and through the ice tongues with very fast ice streams going down these fjords. So this is something that we see in our data from seafloor data that happened in the past with the big Arctic glaciations. Today, Greenland is the only large ice sheet in the Arctic. Other ice sheets are fairly small there on the islands, but in the past, the Arctic Ocean was partially covered and surrounded by enormously large ice sheets. So you can see that the Arctic Ocean itself, actually, it is small already, and due to those glaciations and sea level fall, it turned into a relatively small, like a, well, large preglacial lake, I would say. Almost, not entirely, but to a large extent surrounded by ice. And if I have time, I will show you that actually there was much more glaciations even in this part of the Arctic Ocean. So it was almost entirely encircled by ice during some glacial periods. And moreover, we had ice shelves up to 1 kilometer thick over the entire Arctic Ocean at some point. So it all turned into one huge glacial system, similar in dimensions to the Antarctic, actually. So, about the importance of studying the long-term climate change in the geological record, this is the stable isotope stack, benthic stable isotope stack that shows us the change in temperature and ice volume from relatively small fluctuations in the Pliocene, then becoming high variability and colder altogether. We're migrating through the obliquity cycle Earth to the 100K cycle Earth with very large fluctuations during the glacial Pleistocene and overall much colder. For a comparison, I'm showing here the range of climate change during the historical observations. So you see how that is dwarfed in comparison with what actually happened in the not that long geological past. So in order to understand the variability on various time scales, to understand the full scope of changes and sensitivity of the system and all the feedbacks and linkages involved in it, you really need to go back in time and to do the paleoceanography in order to understand the future and predict it properly. Okay, so the Arctic Ocean is very, very poor actually on the coverage for marine data. It's not that bad for the glacial, for the late to part of middle Pleistocene, but if we want to go further back in time, there is almost no material. If we have material, we don't know how to read it, we don't understand the ages. It's really, really very difficult. This is one example, the mid-Pliocene warm period, which is a very important time slice as an analog for future conditions on Earth. There are a few data points from the Arctic. They're all terrestrial. And there is a very good record from the Canadian Arctic that shows us that the temperature anomaly was huge in the northern polar areas. But we don't have a single data point from the Arctic thus far. No one really understands what happened in the marine. There are models that predict that there was ice-free Arctic, strong draw of water from the Atlantic, but there is not a single core that would be able to at least roughly confirm this. Okay, so when we get the cores, there are all sorts of problems we run into with the proxies and with the age control. The age control, I won't go, I just listed all the major problems we are facing. One of them is the uncertainty with carbon-14. There is paleomagnetic doesn't work in the Arctic as it's supposed to work. Biostratigraphy is very difficult because we have strong dissolution of both silica and calcareous fossils, and because the evolution in the Arctic may have been different from other places on Earth. We don't quite understand the data. So all sorts of complications. As a practical method of stratifying Arctic Ocean sediments, we rely on the color variability in sediments, which is kind of a little childish, but that's the first thing that you do when you split the cores. You see very strong interlamination, brown to more yellowish grayish, brown again, grayish again. Now we know that this is controlled by concentration of manganese hydroxides. We roughly use it. The idea is that more manganese comes into the basin during warm periods with high sea level, because manganese comes from the mainland, from Siberia and especially mainland. Then it recycles on the shelves and goes further into the central basin. So as a rough approach, we just count the layers and count brown layers as interglacials and gray layers as glaciers. By doing this, this is essentially climatostratigraphy. We've developed a reasonable age control, but we are not completely sure about it. That we need independent age control points, which is really, really difficult to get. Anyhow, applying this age model to Arctic Ocean sediments, we were able to get an overall picture of sedimentation rates, which are extremely low in the central part of the Western Arctic Ocean, which is the center of the gyre. We are talking about just a couple millimeters per 1,000 years, or sometimes even less than a millimeter per 1,000 years. So we can only study very, very long-term changes. On the other hand, due to such low sedimentation rates, we can get to very old strata, and we can get a long, very condensed, but long record. If we want to go for higher resolution, we need to come to the margins, which I will mention later. But the margins have their own problems because of sea level drops. Most of the Arctic shelves became dry land, or they were covered by glaciers, which eroded everything that existed on those shelves before the glaciation. So again, very difficult to find a good depot center. So this is an example of course with extremely low sedimentation rates, very slow. And the major feature that you see here, the major lithological boundary, separates the glacial Pleistocene, which has a lot of IRD. This is the photograph, this is the X-ray tomography. And you can see a lot of ice-rafted debris and lamination in the glacial part, because these are glacial interglacial cyclicity with a lot of iceberg-rafted material. But the pre-glacial sediments are very different. They are much more homogeneous, they have much more manganese, they have almost no ice-rafted material, but they have a lot of bioturbation. That immediately tells us that there was much more open water, much less glacial and sea ice impacts. So this is a very exciting, actually. I've been studying for the last several years. I've been trying to focus on that sediment. And we found out that pretty much everything is different in the glacial and pre-glacial parts of the record. I won't go through all of this. The conclusion is that the major controls for the glacial Pleistocene are, of course, glacial cycles and associated sea level cycles. For the pre-glacial, it is primarily variability in sea ice and sea level. So this part is especially important for us as an analog for what is happening in the Arctic today, what we can expect tomorrow. So in a paper that I had a few years ago, I speculated that one reason for this transition from pre-glacial to glacial conditions was the generally falling sea level, so that the Arctic was isolated from the Pacific for longer periods of time because of the Bering Strait. This is the level of the Bering Strait, this blue line. So if you look, there is a gradual glacial buildup and lowering sea level over the so-called mid-Pleistocene transition. And during glaciations, the sea level was getting lower and lower. And the time when sea level was below the Bering Strait silt depth was becoming bigger and bigger. The fraction of time was increasing. So that was one possibility. But probably that's not the only one, because this change is not only regional. It doesn't affect the Arctic only, but it's pretty much all over the northern hemisphere. Around this time, the mid-Pleistocene transition, we have huge changes in the North Atlantic, in the North Pacific. So what we see in the Arctic is pretty much roughly synchronous to changes everywhere in the northern hemisphere. So it had to be also much more global signal in addition. That could be a regional effect on the Arctic as well, but that was one link in the overall chain of events during that time. Now, we have studied one core which we suspected went even deeper in time. And now we have some age control due to the strontium isotope stratigraphy. And there are so far we have not too many data points, but we have more samples in the making to confirm this model and hopefully extend it further down to the, at least to the level where foraminifers completely disappear. And if we can interpolate sedimentation rates further down core, so this core is about 7 meter long core. It covers about 5 million years, so it goes pretty much through the entire Pliocene. Of course, it is extremely condensed. We are talking about sedimentation rates less than a millimeter per 1,000 years. Nevertheless, this is the first record from the Arctic Ocean in which we have a Pliocene, and even with foraminifers preserved all the way down to here, which is really interesting because there was one IODP drilling in the Arctic, in the central part of the Arctic Ocean, but they had a completely dissolved. The entire Pleistocene, Pliocene, even all the way to Eocene, there was nothing carbonaceous. It was a complete failure in terms of establishing biostratigraphy. Starting from somewhere in the lower Pliocene, they started to make dynasties work for biostratigraphy. Otherwise, it was completely blank. So we are lucky to have, for some reason which I don't quite understand, we have preserved calcareous benthic, very rich benthic fauna, very interesting actually, with extinct species. So this is the record, and there are lots of curves just to show you that the major transitions that we see here, one is this early Pleistocene to glacial Pleistocene, with much more variability in the glacial Pleistocene, much more manganese in the early Pleistocene, this benthic forum, very rich benthic forum fauna. So this is the glacial world. This is the sea ice world. And it had to be seasonal sea ice. And we have a lot of phytodetritus forums in those assemblages which indicate that the ice margin was here pretty much most of the time. The ice migrated. So the sea ice had to be seasonal, not perennial, as in the most of the rest of the Pleistocene. And then on top of this, now we identify the Pliocene, which is different in many aspects. You can see there is much less manganese in it. The grain size is different, density is different, forams disappear. All these features suggest the best explanation is that there was a much stronger current activity in the Pliocene. And this is consistent with geophysical records that show a lot of contourites on the slopes in the Arctic during the Pliocene. So that had to be much more open water conditions. Open water with lots of storms, lots of currents coming into the Arctic. Okay, so now, yes, and what happened during the interglacials? The logical question is, okay, these are pre-glacial history. Did it replicate again? Did this similar type of conditions appear during major interglacials? And if you look at these are benthic foraminiferal and planktonic foraminiferal numbers, you can see the peaks corresponding to yellow highlights here. These are major interglacials. So yes, there was a huge variability during glacial Pleistocene. And during some interglacials, we have very prominent peaks of subpolar planktonics in the Arctic, especially during marine isotope stages, well, estimated, 11, 5E, which is logical, and for some reason 5A, which was not a big, it's not even an interglacial, it's an interstadial essentially. Nevertheless, we have a very prominent peak during this one as well, which tells us that the relationship with climate was not simple. There were complicating factors. One of them was possibly the influence of Atlantic waters that would spread planktons, all over the Arctic Ocean during warming intervals. Nevertheless, we did have these warming intervals. They were much shorter in comparison with the pre-glacial, of course, but they did exist. In order to look at the structure of a good interglacial, of course, we should look into the Holocene climatic optimum. First thing that it tells us is that it's not straightforward. There was no even warming all over the Arctic Ocean. So we are, again, having problems. There is a very well-defined warming and seasonally open water in the area north of Greenland. That's where we have most of sea ice today. There's heaviest sea ice in this area. So some people speculated that, okay, if this area was completely ice-free, then the entire Arctic Ocean had to be ice-free, because that's the heaviest ice. But not as simple. We don't see comparable. Now we are mostly studying the area in the Chukchi Sea and the Alaskan margin north of the Bering Strait. We don't see comparable changes in early Holocene in these areas. So that means that the conditions were non-analog to what we're having today. And the reason for that, there are several reasons. There was still lingering Laurentide ice sitting in North America. There was a much reduced Bering Strait flow. There was much more fresh water in completely flooded shelves. So again, we cannot use the Holocene optimum as a good analog for the warming Arctic. It's too many non-analog conditions, non-analog settings. Anyhow, we are focusing now on this area because it has exceptionally high sedimentation rates for the Arctic. The currents are coming from the North Pacific. They're carrying a lot of sediment, and then they lose their energy, and all this sediment is deposited north of Barrow, just a little bit north of Barrow. And there is a huge depositional center sitting here, to which we're trying to, focus our attention. And this is an example of this sediment drift sitting on the North Alaskan margin. This is a bottom profiler record. There are several cores. You can see that the logs are quite similar between cores collected at several areas of this drift. And we have a preliminary age control based on some radiocarbon ages on mollusks. Unfortunately, we cannot collect too many of them. Just where we are lucky, we have a few mollusks here and there. But the data from two cores quite consistently give us average sedimentation rates of about 3 millimeters per year. So if in the Central Arctic we are talking about millimeter per 1,000 years, here we have several millimeters per year. That effectively gives us a resolution of 2-3 years per centimeter thick sample. At some intervals it is even higher, so we are approaching an annual resolution here. And as this area is controlled by the currents coming from the North Pacific, this entire sedimentary record has to tell us a lot about the history of climatic changes in the Arctic North Pacific region. So this is the correlation, the preliminary correlation I've made by using some really quick proxies like the color indices on sediment cores from this area. I correlated them with the dynasist reconstruction of sea ice from another Chukchi core and some ice cores drilled in the North Alaska, in southern Alaska on the Wrangell Range, which bordering the Aleutian Basin. So this is the Bonner-Churchill ice core and the Mount Logan ice core. And there is an amazing similarity in the centennial pattern between the records from the Alaskan margin and the Bonner-Churchill ice core and this diatom sea ice reconstruction. So that tells us, and this record is driven primarily by the Aleutian low atmospheric system, which drives water into the Arctic. So we're getting a linkage between the sea ice conditions in the Arctic and the atmospheric pattern in the North Pacific. And we hope to resolve it by investigating these records in much detail. If we compare the topmost part of this course with the observed extent of sea ice in this particular area during the 20th century, there is an extremely similar pattern altogether, which suggests that we might be able to reconstruct changes and then validate them versus the indices of the Aleutian low variability, indices of sea ice extent in this area, and to maybe understand a better connection between the atmospheric circulation in the region and in the North Pacific, which is actually linked to El Nino on the other hand, because that's to go further away, and sea ice in the Arctic. And for that, of course, we need a very good age control. It's very important, independent age control, and that's the reason why I'm here primarily, because there's practically no carbonaceous material in this sediment. It's almost entirely terrigenous, and we hope that maybe we get some handles to that by using new approaches. Okay, just quickly to show you a very exciting part of my studies that is related to the reconstruction of glaciations in the Arctic. So this is, as I've mentioned, some people speculated that the Arctic had a huge ice complex during glaciations that combined the Laurentide ice sheet, the Eurasian ice sheet, and ice shelves over the Arctic Ocean that kind of linked everything together in one huge mega glaciation. So this was postulated by Grosswald and Hughes. This is a famous publication in Nature. Old-timers must remember that because there was a really big splash. But after a few years, it came out of fashion because terrestrial geologists said, no, there is no evidence for that. I think the mistake of the authors was that they insisted that this system had to exist during the last glacial maximum, and there was no confirmation on that because this is within the range of radiocarbon ages. It was relatively easy to test that on land. And the terrestrial hardcore, quaternary geologists, they said, no way, it's impossible. So this was kind of forgotten for a while until we started collecting really good high-resolution multi-beam and side scan, first side scan sonar, then multi-beam images from the Central Arctic Ocean. That's an example. That's another area in which I'm working. This is the example of a ridge, Northwind Ridge, north of Alaska, like 1,000 kilometers north of Alaska. The water depth here is about 900 meters, and you can see that the top of the ridge is kind of filed away with the grooves completely parallel. There is no oceanographic process that could have done that. It had to be ice moving over and just eroding the tops of the ridges. On the Lomonosov Ridge, which is in the very center of the Arctic Ocean, like practically under the North Pole, we find this erosion at water depth of 1,200 meters. So this is enormous thickness of ice that moved over the Arctic Ocean at some point in the past. The question is when exactly, where did it come from, and how did this ice form? We don't quite understand that. So this is the evolution of our understanding of that. I had a paper in Nature in 2001 that for the first time I've shown then that there was a coherent ice moving over the Arctic Ocean. We found that evidence in several places, in the central part on the Lomonosov Ridge and on the Chukchi borderland, north of the Chukchi and north of Alaskan margin. At that time, I didn't dare to make a reconstruction. I've just shown where we find this evidence, and that's it, stopped at there. Later on, my colleagues and me became kind of bolder, and we started suggesting very conservative. We tried to be as conservative as possible because we were afraid to be criticized that we are followers of Terry Hughes, and as crazy as he is. Okay, so we made very, very conservative. Martin Jakobsen, my Swedish colleague and good friend, he is the major driver of that. He is a guru of multi-beam survey, and he made the map of the bathymetry of the Arctic Ocean, which everyone uses now, IPCA. So he is really a pro in this. We reconstructed ice sheets on the Eurasian side with possibly ice going over to the Lomonosov and the Laurentide ice moving over the Chukchi borderland. Then the ice was growing and growing in our reconstructions, and finally Frank Nissen from AVI, he, for the first time, has shown on the map what we have suspected always, that it existed there, but we were not sure. He has shown that there was a very large, not huge, but very large ice sheet sitting on the East Siberian shelf as well, in addition. So as a result, practically the entire Arctic Ocean was encircled by glaciations. So I'm trying to focus on this area, including the Chukchi borderland, northern part of the Chukchi shelf, all the way to the Alaskan margin, and the East Siberian margin as well. So to understand the interaction, because if this is right, if we did have an ice sheet sitting here, there was a very interesting interaction of ice coming from the Laurentide side and from the East Siberian side. So I'm working on this area, and we had a paper recently with Dayton Dove on the Chukchi Sea and contributed to a big compilation of martins in 2014, in which we basically show that the entire Chukchi shelf is also eroded by ice. And there are several generations of erosion. We don't understand the stratigraphy well enough, but we do understand the pattern of the movement of ice from seafloor morphology. And I suggest that there were three major ice centers that affected this area. One was the Laurentide, with ice coming all the way from the Canadian Arctic archipelago along the Alaskan margin, maybe shouldering and affecting the northern coast of Alaska into the Chukchi borderland. The other one was coming from the East Siberia. There was a big ice sheet sitting here, with ice moving onto the Chukchi borderland as well and on the Mendeleev Ridge. And the third independent center was on the Chukchi Sea itself. We don't know how far south this ice went. We have a little bit of, because mostly we rely on multi-beam bathymetry and subbottom profiles. None of them works in shallow areas, because shallow areas are all smoothened by the sea level rise. First of all, everything is turbated by icebergs, then it's smoothened by sea level rise. There are sands that are unpenetratable for the subbottom profiler. But we've got a little bit of a sparker imagery in this area that shows that there are huge tilts underneath that increase in thickness southwards. So I will not be surprised if some of these glaciations, not the last one definitely, but some of the older glaciations extended all the way into the North Pacific, over the Bering Strait and into the North Pacific. Quite possible. So this is to show you, these are the cores on which we are working, and Yamamoto-san is working on some of these cores. I'm collaborating. The Germans are working on this course also. I'm working on this area. A lot of these cores were collected from the Korean ship, the Araon, on which I've been working for the last several years with colleagues from the Korean Polar Research Institute. And just different color coding is for different glaciation that we identified. The yellow is the LGM extent. So the LGM is very restricted. It is in shallower areas, and the ice was definitely coming from the Laurentide ice sheet. But the older glaciations are found all over the place at much deeper water depths. So that tells us that the last glaciation was actually much smaller in the Arctic in comparison with previous glaciations, which is strange, because you would expect the LGM was a huge sea level fall. You know, everyone knows that it was enormous glaciation, but the Arctic has its own life. You know, we don't quite understand why. This is really interesting for modeling. I've had several proposals submitted. None of them was funded so far, but as long as I keep working, I will keep trying. All right, this is just an example of some of the beautiful subbottom profiler records, and you can see this huge flows of sediment that was pushed by ice from the margins. So these are kind of debris lobes coming from the margins into the deep basin, and then we can extend the stratigraphy. And this is an example of a long core, 14-meter long core we collected in the center of the Chukchi Basin. And we can relate these layers to the debris lobes on the slopes, and trying to reconstruct the history of glaciations, understanding the stratigraphy, the provenance, and eventually how they were formed, how they were propagated. And of course, in order to better understand the history of this region and deposition here, we need a real drilling. And there were several pre-proposals in the system. One of them submitted by myself with Julie Brahim-Greta for these areas. None of them was developed into a full proposal so far, because there are so many questions. We've been working on this pre-proposal, I thought this is simple and straightforward. The more I've been working on this course and on this data, the more I'm lost. I don't know where to go. I cannot even find a good site for drilling, because there are so many complications. But now my colleagues kind of convinced me to write a new proposal focusing on this depot center north of Barrow, just for the Holocene, to drill a very, very high resolution, the complete pile, which is almost 100 meters. So that would be really interesting, although these sediments are difficult to work with. Once again, they're mostly terrigenous, very fine-grained sediment, difficult to date. This is a drift. Nevertheless, this is an exceptionally high-resolution Arctic record, the only one. There is no other one. And so maybe we will try to submit a new proposal by the October deadline for bringing the drilling expedition to this area, which is getting more and more feasible because sea ice retreats much further north. So this is practically an open area, open water in summer now. On the other hand, it is less, as I've said, it's less predictable. You can have open water, and then strong wind will bring a huge ice flow from the north, and that's really impossible to predict. When ice was more solid around, it had a regular pattern, it was predictable, but now it is really whimsical. So to just summarize the framework of the Arctic sea ice and related history, the major steps that we have kind of tentatively identified is the Pliocene was mostly ice-free, very strong currents, very strong storminess, which is something that expects us in the future, of course, and has a huge effect on the Arctic. Early Pleistocene, we had mostly seasonal ice, transitional conditions. Then glacial Pleistocene, mostly perennial sea ice plus ice shelves during glaciations. Huge impact of ice sheets on the Arctic Ocean during glaciations, reduced ice at the interglacials, especially at some intervals. We don't quite understand the relationship with climate. There was a complex response, probably in relationship to the current system. And then in the Holocene, the focus is on the late Holocene. We see high-frequency variability, which is subdecadal to centennial, but that variability is superseded by the modern change since starting from the mid-20th century, there is a much more unidirectional pattern, with that high-frequency variability preserved, but now it is superimposed on this trend. So, well, I think I'll stop here because you are tired probably. I wanted to show you just does not require much attention, just a few cartoons showing what we can expect from an ice-free, at least seasonally ice-free Arctic. What will be the major effect? Well, one is obviously effect on the biota, because the biota in the Arctic is unique. It is all somehow tied to sea ice. Starting from, tiniest creatures, the phytoplankton, and all the way up to polar bears, it's all related to sea ice this or that way. So disappearance of sea ice or the change of the yearly cycle will have enormous effect on the biota and biodiversity. Another big player is acidification. It is coming already, and it will come big way, of course. As the more sea ice melts, the more stronger will be acid. And the warmer the water is becoming, the stronger acidification we will get in the Arctic. Another one, huge one, is storms that are coming already. In the past, working in the Arctic was in many ways easy because as soon as you get to the ice, this is the calmest weather you can expect. The ship is steady except for bumping. Ice bumps you around, but there were no waves, no. Last several years, we had a double whammy. We had ice, and you could have ice and storms at the same time. So that's a hell. And of course, that increases the coastal erosion immensely. These are some examples from Barrow. You can see that the houses disappear close to coastline. There are berms that need to be done here. The fortification of the coast, but even that won't help, because also consider that most of those coasts are made of permafrost, and it melts away very fast. So it's a huge degradation of the coast. Then another very interesting one is the shipping routes. If you consider that shipping from North Pacific to Europe via the Arctic is like 3 times faster and 3 times cheaper than going around Asia, through the Suez Canal and all that stuff. So it has enormous importance economically, and that's one of the key reasons why the Pacific countries are so interested in the Arctic. In addition to the academic interest, they're interested in climate, of course, because it affects them strongly. But also countries like Japan, China, Korea, they invest into Arctic research a lot because they're really keen on knowing when they can start shipping across the Arctic. There is a limited shipment. It's possible to go, but you have to go through Russian waters, and Russians charge enormous money for icebreakers. You cannot go there on your own. You have to hire an icebreaker from Russians, and you pay a fortune for that. So they're all waiting for the time when ice will retreat further north and the shipping lanes will migrate into international waters. That is a really game changer. So understanding when will that happen is very important. People are modeling that, and this is an example of models that show the frequency of routes, and you can see that later, in this century, we can expect ships going like directly straight across the Arctic Ocean. And that's really important. And of course, one of the consequences of this is contamination, because the litter is already entering the Arctic Ocean. These are a very interesting paper, actually. This is from the Fram Strait. That's the connection between the Arctic and the North Atlantic. A lot of ships and a lot of tourist ships that go to Svalbard are passing through Fram Strait. And this is the result. There is more and more litter accumulating on the Arctic seafloor, and it will move into the Central Arctic with opening sea lanes. It's kind of symbolic that the first freighter that passed through the Northwest Passage, through the Canadian channels, they became open several years ago. It's possible to go through, maybe not every year. The first freighter was carrying coal. So it's really sad and ironic. Another really big issue, of course, is oil and gas in the Arctic, because the Arctic Ocean floor has a lot of oil and gas potential, especially on the shelves. Not as much in the Central Arctic Ocean, but on the shelves. The Russian shelves are incredibly rich in oil and gas. The Barents, part of the Barents Sea and the Kara Sea, they have enormous deposits there. The Chukchi Sea has quite good deposits, and the Eastern Siberian, I think, is underestimated, actually. Now they have better estimates. Now what is happening is, the Russians had a deal with Exxon, which is not less than $500 billion bill. They were supposed to drill on Russian shelves, and these are the major, exploration areas in the Kara Sea, huge areas. I've been working a lot in the Kara Sea, so I know that situation pretty well. Now we cannot, even my Russian colleagues have hard time accessing those areas because this is all commercial, and you can't get in there. And there are quite large areas in the East Siberian and in the Chukchi. So that deal was killed by the sanctions against Russia after they invaded, Crimea and eastern Ukraine. This was all killed. But now, with Rex Tillerson becoming foreign minister, and with the game change, it's almost for sure that at least sanctions related to this will be removed at some point. It's not that easy. It has to be pushed through Senate, but I think they will do that. And so this is what's awaiting us, a big oil exploration. And what does that mean for the Arctic, in addition to the global implications, of course, the greenhouse effects? Pollution in the Arctic is very, very dangerous because cleaning it is much more difficult than in lower latitudes. So this is a very interesting, this was the mapping of the BP-size oil spill for the Arctic, considering only at that point they didn't consider the Arctic, exploration area, but only the northern Alaska, like the Dead Horse and the Exxon Valdez, and the areas in the Chukchi Sea where there is drilling for oil, planned drilling at least. And this is how the BP-size oil spills would look like in the Arctic. And it's extremely, they don't even really understand well how to clean it in the ice conditions. So that's, well, I will stop here. And I'm sorry if that was a little bit too long, but it's hard to stop. It's so exciting.